switch this, hopefully. And yes.
Okay. Thanks. And thank you very much for the invitation to give a talk here. So I'll start with a disclaimer. I am absolutely not a PETSc expert. I am not even an expert at writing software. What I enjoy is designing parallel linear solvers and proving that they are going to converge. But luckily, Loïc Gouarin joined our team at École Polytechnique. So we were able to write a PETSc demo code, which you can get from his GitHub page. And so he has done all the PETSc numerical results with me. So in the spirit of what Matt said yesterday, our code is available on the GitHub. So the link is there. You can either download it and install it, or you can run it on a binder. So this works more or less well depending on how many people are using the servers. Okay, so I'm not going to do that today, and I'll switch off my Wi-Fi. So what is in our code is really three things. So we have domain decomposition, preconditioner. So I know that there are some DD preconditioners there, but for simplicity, we just started by adding another one to figure out how things are working. And so by default, it is BNN. You can switch to additive Schwarz with this option here. In all cases, it is non-overlapping subdomains, or in the case of additive Schwarz, what we call minimal overlap. The second thing that is in the code is the GenEO coarse space, which helps with convergence of the domain decomposition methods. And the third thing is the adaptive multi-preconditioned conjugate gradient solver. So if you don't know what these things are, that's fine, because the outline of my talk is basically to go through all of these things. So we start with an introduction to domain decomposition and to domain decomposition in what we call the abstract Schwarz framework. So if you don't know about domain decomposition, this is the book that you should be reading by Toselli and Widland. So if we're given a problem, which is to solve AX stars equal B with a symmetric positive definite matrix, we can define a whole lot of domain decomposition methods by doing the following procedure. So the first thing you need to do is you take your computational domain omega and you partition it into subdomains. Okay, so that's pretty simple. Here the domain is the unit square, and then omega S in pink here is just one of the subdomains. So throughout the talk, S will always be a number between 1 and capital N, which is the index of one subdomain. Then you need to define interpolation operators, RS and RS transpose, which are the restriction and prolongation operators. So they take a local quantity and extend it by 0 to the entire domain, or they take a global quantity and they just cut the parts that is in omega S. So that's the second ingredient, and the third ingredient is you need to choose your local solvers. So the local solvers are these AS tilde matrices or operators. So they are local, they live in the subdomain, and they are very important since they appear very crucially in the definition of the preconditioner here. So the preconditioner will always be H. It is the sum of the local solves AS tilde minus 1 with the right interpolation operators. Okay, so I guess you're all pretty much familiar with this. You can already do this in PETSc. If you use the preconditioner type ASM, then for example, you can come and plug in the AS tilde, the local solver that you choose, with this get ASM sub KSP, and then set the type to your AS tilde. Okay, so this is a large family of methods, and there are a few ones that stand out and that we use more often. So the first one is the additive Schwarz preconditioner or domain decomposition methods, where the choice for AS tilde is RSA RS transpose. So this means that you take the global matrix A and you come and you catch the degrees of freedom that are in omega S. So you get a block of the matrix that corresponds to the degrees of freedom for that subdomain, and then if you plug that into H, Well, basically what you're getting is very similar to a block Jacobi preconditioner, except you have overlap between the blocks, because the degrees of freedom that are on the interfaces between subdomains belong to several subdomains. Okay, so that's one possible choice. Another possible choice is to do Neumann-Neumann or balancing Neumann-Neumann, which we call BNN. And then in this case, the choice for AS tilde is a bit longer to write. So AS tilde, there's a DS matrix in a DS inverse. So DS is just a diagonal matrix, such that if you put all these DS's together, then you get a partition of unity. Okay, so these are just diagonal matrices that have weights in them that tell you how you share the degrees of freedom that are shared by several subdomains between the subdomains. So that's the first ingredient, and the second ingredient is the local matrix A restricted to omega S, which is the matrix that you get if you assemble your problem on subdomain omega S instead of assembling it on the global domain omega. So that's also quite standard. So this weighted Neumann matrix, then if you plug it into the preconditioner, you get the BNN preconditioner. But you can do anything really. So for example, the default choice in PETSc for the ASM preconditioner is to choose AS tilde to be the ILU0 factorization of the block that corresponds to omega S. So all of these are domain decomposition methods. They can all be written in this abstract Schwarz framework. So this is all very simple. We do tend to make things more complicated since we very rarely use just a plain domain decomposition method. We usually use what we call a two-level domain decomposition method. So this is also known as a domain decomposition method with a coarse space or a deflated method, a projected precondition method, or the balanced method. So this is where the balancing in balancing Neumann-Neumann comes from. So all of these are names for the same idea, which is that you are going to define a coarse space by choosing a set of coarse vectors that you put into U, then span of U is the coarse space. You define a projection operator. This pi here is an A orthogonal projection. So you do it so that this part here is the projection onto your coarse space, and then your problem AX star equals B is equivalent to two independent problems. One is your coarse problem, which you solve in the setup step with a direct solver, and then the remaining problem is going to be solved with the precondition conjugate gradient algorithm. Okay, so now instead of solving AX star equal B, well, we have our preconditioner for starters, and then we have the projection preconditioner pi. Okay, so this is a two-level method because every time you do a step of PCG, you apply H on one level, and then you have to do the projection, and in the projection you do a coarse solve, and that is the second level. Okay. So why do we do these two-level methods? Well, there are two main reasons to use a coarse space. The first one is to make operations well-defined, or what I mean by that is that I sort of cheated before when I introduced the BNN preconditioner because I introduced this operator here. This would be the AS tilde inverse, except that I can't actually invert the AS tilde, because this A restricted to omega S has a kernel for all floating subdomains. Okay, if you're solving for the Laplacian, then the A of phi I phi j is gradient of phi I dot product gradient of phi j. So for example, the constant will be in the kernel of those operators. Or if you're doing elasticity, like we're going to do later, you get the rigid body modes. So you have to replace the inverse of this matrix by a pseudo-inverse, and then somehow you have to deal with the fact that you are not handling the kernel of the matrix, and that's what you do with the coarse space. So what we call the natural coarse space is the coarse space that has in it the kernel of all of the local operators A tilde S, and we just, of course, have to prolongate to the global domain. So that's the first reason to use coarse spaces, and the second reason is to improve convergence, but we'll see more about this later. So what about the what can be said about the natural coarse space? So this is an example, but I have a new example in PETSc. So this is going to be sort of our toy problem. If you run the code that is on GitHub, this is the problem by default. So it's a 2D elastic beam. You have two materials. You have a soft material in purple, and then you have layers of a harder material going through. Okay, and I solve this with my different algorithms. So these are 4 subdomains. And if I show you the solution, this is the solution. Okay, so I have clamped the beam on one side, and then I have gravity. And of course, this is a big exaggeration of the displacement. Okay, so that's our test problem. I can now choose the values of the red and the purple material parameters. So in the first test case, I'm going to have a constant material. So this means that I set both material properties to 1, and then I get fast convergence. Okay, all I need to do to break that with the natural coarse space is to add heterogeneity between 2 materials, and then this breaks convergence, and we get far more iterations. So the natural coarse space somehow is not enough to guarantee a fast convergence of the DD algorithms, and that is what we go on to fix with the GenEO coarse space. Okay, so the idea of the GenEO coarse space is really quite simple, and to introduce it, I'm going to start with this sort of ideal coarse space. So if I could choose exactly the vectors that I wanted for my coarse space, this is what I would do. So first, we know that we have a bound for the convergence of the preconditioned and projected conjugate gradient algorithm, which is this bound here. So it tells us that the error at iteration m of the algorithm divided by the initial error is smaller than some quantity that depends on the iteration number and the condition number of the preconditioned and projected operator HA pi. So if I were able to compute the spectrum of HA, that is, gets all the eigenvalues lambda k and eigenvectors xk, then I could just choose a target condition number, kappa target, by choosing a lambda max target and a lambda min target, and then put into my coarse space the eigenvectors corresponding to eigenvalues that are either too large or too small to get this kappa target. Okay, that's something I could do. Then for the problem in blue that I solved with PCG, I would get the convergence bound with my target condition number plugged into it. So essentially, I can converge as fast as I want. Now, of course, it's not realistic to compute the spectrum of the preconditioned operator when you're trying to solve a linear problem, and so you can't do that. But what we do with the GenEO is almost as simple. We just add one extra step in there, which is to use the properties of the domain decomposition algorithms. So DD has been around for quite a long time, and there are some very nice theories for the convergence of DD, and so this is one of the results. So we're first going to focus on the upper bounds for the spectrum of the preconditioned and projected operator. So what the results from the theory tells us is the following. So if for every vector xs, I can prove this estimate here, for some constant omega, I get that the norm of xs induced by the RSA RS transpose operator is smaller than omega times the AS tilde semi-norm of xs, where AS tilde, again, is just the matrix that we chose in the preconditioner. So if I can prove that, then I know that all eigenvalues are smaller than n times omega, where n is just an additional constant which corresponds to the maximal multiplicity of 1 degree of freedom. Right. So in some cases, we can prove this result by going back to the PDE. In many cases, we can't. And anyway, we don't want to make assumptions about the PDE. And so instead of trying to prove it, well, we choose a lambda max target, which will give us an omega target that we need to prove the estimate for the omega target, and instead of proving it, we just identify which vectors satisfy it or not. So to do this, we solve a generalized eigenvalue problem in each of the subdomains, and the matrices in the pencil of this generalized eigenvalue problem are exactly the same matrices as in the bounds we're trying to prove. Okay, so very simple. We compute the smallest eigenvalues of this eigenvalue problem, and then we put in the eigenvectors, which are prolongated to the entire domain for all eigenvalues that are smaller than this number here, which depends on our target. So that's for the lambda max. Now, if you have been paying attention, you may have noticed that the operator RS transpose in blue up there is exactly the operator that we used to define the additive Schwarz preconditioner. Okay, recall for additive Schwarz, we have this here, so that means that this eigenvalue problem is not going to tell us anything. We're just going to get eigenvalues that are equal to 1. So it doesn't help us out, but also if we plug the AS tilde into the bounds up there, we see that the estimate holds with omega equal to 1. So essentially what this says is that for free with additive Schwarz, you get that all eigenvalues are smaller than this constant n. And you don't need to do any extra work for the coarse space. Now this slide is about to become a bit full, but I'm going to add now what happens for the lower bounds of the spectrum. So I have a theoretical estimate, which is here, so it's similar to the first one. Again, we have these two energy norms or semi-norms, and the matrix, the weighted Neumann matrix, pops in here, and I just add a second eigenvalue problem in each subdomain, and then a second way of adding vectors to the coarse space here, which are eigenvectors coming from the eigenvalue problem for the lambda min. Right, so if I do both of these, then I have guaranteed both the bounds on the spectrum, and I can guarantee fast convergence. Now the remark this time is that the matrix that appears here and then again in the eigenvalue problem is exactly the AS tilde that we had for B and N. So for B and N, this eigenvalue problem tells us nothing, but the estimate tells us that lambda min is larger than 1. So if you take any matrix, any AS tilde, you have to solve 2 eigenvalue problems, but if you use additive Schwarz, you only have to solve 1, which is for the lambda min, and if you use B and N, you only have to solve 1, which is for the lambda max. Okay, so these are the references to the original GenEO papers. The first one is actually the one that is dated 2014 with Vitorita Dolean, Patrice Auré, Frédéric Nataf, Clemens Pechstein, and Rob Scheichel. Now, this is very closely related to Stefano's codes for BDDC with the adaptive choice of constraints, where the same ideas are sort of used to build a coarse space and guarantee convergence. And GenEO is also a part of the HPDDM software. So at this point, I want to make one important remark, which is something that I have mentioned, but I sort of flew over it, and this is that we do need a lot of information on our problem. We need more than just a global matrix A, because we need to be able to assemble the problems over the subdomains. So basically, in PETSc language, what I'm saying is that we need the matrix in MAT-IS format. Okay, so now I can run my example. So I can run it here. This is the heterogeneous problem I had earlier, and if I turn GenEO on, so turn it on true, then I get very fast convergence. Okay, just 5 iterations. And here I have plotted a whole lot of information, so if I look at what the algorithm is telling me, it is telling me for some subdomain, say this one, these are all the eigenvalues that were computed for lambda max. So I selected the first 8. I also had 3 coarse vectors that were coming as 0 energy modes of the local operator, because this is B and N, and so in the end I assembled a coarse space of size 50 and got fast convergence. Okay, so that was solving it using the the PETSc CG, and now I'm just going to move to here, and I'm going to solve the exact same problem with our own solver, and then this is going to allow me to plot some information. So we're not getting exactly the same behavior as previously because I changed the thresholds, I changed the lambda max targets to 1000. Okay, now I see that, for example, in subdomain number 1, I will have my 3 rigid body modes and then 3 vectors coming from the eigenvalue problem. So I can plot these, and this is what I'm going to do here. Okay, this is just a solution again, and then I can plot the coarse vectors. So I will show you the materials. So the first coarse vector is for subdomain 0. Okay, I have 2 for subdomain 0, and then from here on we are on subdomain number 1. So the first coarse vector is just a rotation of that subdomain. So it's a rigid body mode for that subdomain. Then I have this one here is also a rigid body mode. This one is a rigid body mode. Then eigenvector number 5 for subdomain number 1, and just show only that domain. And you see that it is basically the rigid body mode of this layer of hard material. Okay, and then this is confirmed if you look at number 6. Again, rigid body mode of the layer of hard material, and the last one. And then coarse vector number 8 is for subdomain number 3. Okay, so you can plot these eigenvectors and see what comes out of the GenEO core space. Right, so anyway, we do get the fast convergence that we expected. Now, the only drawback to the method is that you have to do the computation of the eigenvalues in the setup phase. Also, you have sort of strong assumptions on the fact that your problem, that the idea for the GenEO core space comes from the convergence bound for PCG. So if you wanted to extend this to other linear solvers, say maybe solve a non-symmetric problem, well, then I don't really know how you can extend that. So we have tried to produce the same information in a different way, and this is what we do with the multi-preconditioned algorithms. So before I tell you what the multi-preconditioning is, I need to remind you of some properties of the usual PCG algorithm. So we're solving AX star equal B, and we have a preconditioner H. Now what the PCG algorithm is going to do at iteration I plus 1 is that it is going to return the approximate solution xi plus 1 that minimizes the error here over the space that is the previous approximate solution xi plus something in the span of the preconditioned residual. So I put a tilde because I do know that there is an orthogonalization step, but let's forget about this for the moment. So you start at your previous approximate solution, you add one search direction, and then you choose the point on that line that minimizes the error. Okay, so the idea has been around for a long time that if you use a larger minimization space than just one direction per iteration, then you can get faster convergence. So if you think about it, that is sort of what we did with the deflation or the core space, where we initialize the algorithm with a minimization space that is the core space. So we enlarge it before we start solving, and then we add one direction per iteration. Another way of enlarging the minimization space is to use the Bloch-Krylov subspace methods. So you've probably heard of block CG, and then multi-preconditioning is a different approach. So with multi-preconditioning, instead of having one preconditioner H, we assume that we have n preconditioners, which are numbered H1 to Hn. Okay, so n preconditioners, and then the way to compute the approximate solution xi plus 1 is to minimize the error x star minus xi plus 1 over the space that is the previous approximate solution plus all the vectors that are spanned by these preconditioned residuals. So you're doing the same procedure, except you have a larger minimization space, and of course the tilde is to say, again, we are going to orthogonalize. So this is the original multi-preconditioned CG paper by Britson and Greif in 2006. And they immediately pointed out that domain decomposition is a very natural application for multi-preconditioning. The reason is that all the domain decomposition preconditioners write as a sum of local solves in the subdomains. So what you can do is, instead of computing the sum here, you can keep each of these contributions separate. And so now instead of having one global preconditioner, you have n sort of local preconditioners. Or at least they are local contributions to the preconditioner. And you can do this with any DD methods, and I will show results with BNN. Now here is the literature. So as I said, this is the original MPCG paper. Now I started working on MPCG with Daniel Rixson, and he had presented the idea for Fetty in his PhD thesis. And there is also a multi-preconditioned GMRes method, which is in these papers here. Okay, so it's not a very well-known method, but we are getting good results with it, so I think it's an encouraging method. So let's look in more detail at the MPCG algorithm. So again, AX star equal B, we have our n preconditioners H1 to Hn. And here on the left-hand side, I have MPCG, and on the right-hand side, I have PCG. This is just to show you that they are pretty much doing the same iterations. So of course, we start with x0, which is our initial guess. We compute the initial residual B minus x0, AX0, and then we go on to preconditioning. So on the right-hand side, we apply the preconditioner H, and on the left-hand side, we multi-precondition, which is we apply our n preconditioners and we stick them into a block of vectors. Okay. Then as our search directions, we use either this block or just a single vector. Then once you enter the loop, the first thing that you do in the loop is to update the approximate solution. So xi plus 1 is equal to xi plus an element which is in the span of pi. And of course, what we do here is just to compute the coefficient alpha I that minimizes the error. Okay, so here alpha I is a scalar, and here alpha I is a capital N size vector. Then when you update the approximate solution, well, you also update the residual, and then you're ready to prepare for the next step by either preconditioning or multi-preconditioning, and then orthogonalizing against previous search directions. So something very unfortunate happens here, which is that we lose the short recurrence property, and we have to orthogonalize against all previous search directions. So that's why there's a sum here. Okay, so sort of the magic that happens in CG doesn't happen in this case. So the difference with PCG is that the preconditioned residual and the search directions are blocks of vectors. The similarity with PCG and difference with block CG is that we still only have one approximate solution and one residual and also one right-hand side. Now the properties that we can deduce very easily from the algorithm are the following. So we have the global minimization property. So at iteration I of the algorithm, the approximate solution xi minimizes the error over this space, which is x0, plus the space which is spanned by all the search directions up to that point. So we minimize in an I times n dimensional space. So that's what we were, of course, aiming for, was enlarging the minimization space. And then, yeah, we do have that the blocks are pairwise A orthogonal, but that's because we explicitly orthogonalize. So here is an example that I will show you. So this is the Octave and FreeFem++ implementation from my paper. So again, it's a 2D elasticity problem where we have two materials that are shown here. So we have a red material and a yellow material. There's a jump in one of the coefficients, and this is a partition into subdomains that I got with Metis, so I'm cutting through all the jumps. So I solved this with the different algorithms. So first I solved it with BDD, Okay, so BDD is an implementation of BNN where you eliminate the degrees of freedom inside the subdomains, but you can think of it as being BNN. And so for this problem, the BNN is quite slow. So this is, again, the observation that the natural coarse space is not enough to guarantee fast convergence. Then I solved it with the BNN and the GenEO coarse space, and these are these green circles. And then, of course, I got fast convergence because I had pre-computed the coarse space. And now what's new here is that I solve also with the multi-preconditioned algorithm, and I get very fast convergence also. Okay, so this is reassuring in the sense that the algorithm is leading to a fast convergence in terms of the iteration counts. Now, the reason that we are converging in very few iterations can be understood here, where I plot the size of the minimization space with respect to the iteration count. So with BDD, I start at the number of rigid body modes, and then I add one vector per iteration. With GenEO, I start with the size of the GenEO coarse space and add one vector per iteration. And with the multi-preconditioned, I start at the same place as with BDD, but then I add 81 vectors per iteration. So I am building a minimization space that is really quite large. However, it is not completely crazy to do this because the directions in our minimization space are local. So if you remember, when we defined our preconditioners H1 to Hn, each of them was a local solve, with just the interpolation operators. So this means that the directions that I'm adding are local instead of global. And so here I counted the number of times that I had to solve a local problem, either to apply the operator or the preconditioner. And even though I have a larger minimization space, I am actually doing fewer local solves than with BDD. Okay, so that's one indicator that what we're doing is probably not too expensive. So this is an industrial test case that was computed by Christophe Beauvais at Onera. So it's an elasticity problem. It was solved with the domain decomposition methods PETSc. So if you don't know PETSc, it's a bit painful to write down all the algorithm because there's quite a lot of notation, but the ideas are really the same ideas as with BDD. And so getting a multi-preconditioned version of that is very simple. So these spheres here are all little spheres of solid propellant. So they all have different properties. And then he solves the problem with multi-preconditioned PETSc. This is the convergence curve that he got. So there's nothing to compare it against because it's a case that simply didn't converge with the usual PETSc algorithm. Okay, so the multi-preconditioning really does help with robustness of domain decomposition. Now, if I look in more detail at the timers here, so we see that we spend a lot of time in this light blue part, which is the orthogonalization step. So essentially, most of the time we spend running our algorithm is spent dealing with the fact that we have all these search directions and we need to orthogonalize them. And this is becoming it takes a lot more time than the local solves, which are in the preconditioner and the operator. So this means that we have only half solved our problem and gives us the idea to add adaptivity to the algorithm in order to not get such a big minimization space. So the ideas for the adaptivity are the following. The first one is that it does seem that these local contributions, these local preconditioners, lead to a good minimization space since we get the fast convergence. Now the drawback is that we're getting very many search directions and we have to orthogonalize them. And we know from the previous work on the GenEO that if we can find the right set of vectors, then just a small number of vectors are sufficient to ensure the fast convergence. So can we find these within the multi-preconditioned algorithm? So the answer is that yes, we can, but there is one condition which is very important, and this is that we have to have a lower bound for the spectrum of our preconditioned and projected operator. So essentially what I'm going to say next applies to BNN, but does not apply to additive Schwarz. Okay, so this is the adaptive multi-preconditioned algorithm. So it's the same setting as previously, except that now the user has to choose some number here, tau. Okay, you have one parameter. So for example, I think tau equals 0.1 is the default in the code. And then what the algorithm does is that it has a preconditioning step here in blue, which either does a multi-preconditioned iteration, in this case here, or it does a preconditioned iteration, in this case here. And we have a test, which we call the tau test. I'll tell you a bit more about that on the next slide, which allows us to decide which kind of iteration we are going to do. So there's no problem mixing both types of iterations. The global minimization property still holds. The only difference is that now we don't know in advance what the size of the minimization space is going to be. It can be anything between the iteration number and the iteration number times the number of subdomains, depending on what the algorithm has decided to do for that particular problem. So what can I say in terms of the theory and how do we choose the tau test? So the theoretical result that we can prove is the following. If the tau test returns that Ti is larger than tau, so that is that in the preconditioning step, the algorithm decides to do the usual preconditioning instead of the multi-preconditioning, then we can guarantee that the ratio in the error at between the two previous iterations is bounded by some quantity that depends on tau. Okay, so this tells you how you can choose tau. You can say, I would like to decrease the error by 5% at each iteration. Then you get tau equal something very close to 0.1, and that tells you how you set tau. So I'm not going to go into the details of the proof of this result, but I mean, it's a very short proof. It just uses the properties of the preconditioned conjugate gradients algorithm. You do use, quite crucially, the fact that you have a Rayleigh quotient, which makes the smallest eigenvalue of the preconditioned operator appear, and then you replace that by 1. Okay? And then you have another term in the bounds for the ratio between the errors, the two errors, and this one you don't really know what to do with, so this is what you plug in as your Ti and see whether it is smaller than or larger than tau up there. Okay, so that was for the theory. Now I'm just going to very briefly say that, of course, you can also decide, instead of doing either a preconditioned or a multi-preconditioned iteration, you can decide to do something in between. So you can say, at this iteration, I am going to keep the direction that is coming from subdomains 5, 10, and 15, and add all others together, and we have a local test to decide what to do in each subdomain. So this is with the idea of reducing even further the number of search directions. Right, so now some numerics. So this is not the most impressive test case, I have to admit, but it is quite an important result. If I solve our test problem with the materials again, and then this time I have a regular partition into subdomains. So this means that I only have one material inside each of my subdomains. So this is a problem that we know to be easy for domain decomposition methods, and I can see it here. So for all methods, convergence is very fast, including the usual BDD methods. So what I'm checking for here is that in the methods that are adaptive, where I choose either a coarse space or I choose what kind of iteration I do, the algorithm is recognizing the fact that the problem is already easy and it is not doing more work than needed. So we do get that. We see that all the curves sort of are the same here for all the adaptive algorithms. We don't have a larger minimization space. And of course, the only one that stands out is the fully multi-preconditioned methods, which is not adaptive. So that is reassuring in a sense. We're not going to work too hard for a very easy problem. Now I go back to the case where I have the irregular partition into subdomains. And so I solved now with both versions of the adaptive multi-preconditioned algorithm. Convergence is very fast, much faster than with BDD. So this is just the same, but removing the curve that was slow. So it's sort of a zoom into the new methods. And yeah, so essentially all the adaptive methods converge in the same number of iterations. And then if I look at what happens with the minimization space here, well, something very interesting happens. So if I look at the orange squares, this is the adaptive multi-preconditioned BDD with the global tests. So where I do either a preconditioned iteration or a multi-preconditioned iteration. And looking at the dimension of the minimization space, what I realize is that during the first 4 iterations, I'm multi-preconditioning. So I'm adding n search directions per iteration, and then here something very nice happens, and the tau test detects that we have found all the sort of problematic vectors, and now convergence is just fine with the usual PCG, and we go on to add just 1 vector per iteration. So basically what's happening is first we multi-precondition, and then we have sort of constructed a coarse space on the fly, and then we can revert back to preconditioning. And this doesn't show very much in the convergence compared to the fully multi-preconditioned algorithm. So the adaptive process seems to be doing its job. So now I have a few more tests, but I just want to show you that this is also in the code. So this is the same problem as previously. So this time I turn GenEO off with GenEO by setting GenEO to false, and I turn the AMPCG on by choosing tau equal 0.1, and I solve. And then this is what comes out. So we still have the natural coarse space. So the rigid body modes are still in the coarse space. We'll always have that for BNN. And if I look at convergence, so it is quite fast, 14 iterations, and maybe most importantly, only the first 3 iterations are multi-preconditioned, and then the algorithm stopped multi-preconditioning and did the cheaper version of the iteration, and that was sufficient. Okay, so if you want to play with the parameters, there are a few more things you can do, and they are shown in the notebook. So very fast, this is a weak scalability test that we present in the paper here with Christophe Beauvais, Pierre Gosselet, and Augustin Paré-Friot. So I think Augustin ran this one at Safran-Tech, which is a French aerospace company. And yeah, so we have 1,400 nodes, and we compare the usual PETSc to the adaptive multi-preconditioned variants, and we have really improved the weak scalability. Okay, so one final test that I'm just going to tell you what the conclusion of this test is. So Augustin here, what he did is for this composite material, he looked at what happens if you increase the jump in the coefficients, and if you solve with PETSc, so this is in blue, then the convergence gets a lot worse when you increase the jump in the coefficients, whereas with the new algorithms, essentially nothing much happens when you increase the jump, and then this is another weak scalability test. Okay, so that is what I wanted to present to you. So I presented 2 ways to improve the robustness and efficiency of domain decomposition algorithms, which are the GenEO coarse space and the adaptive multi-preconditioning. So there are 2 different things. You can also use them both together if you want to. And yeah, I have added some perspectives, but I'll stop here. Thanks for your attention.
We have time for some questions before we cut to coffee. Barry.
Do you think there's a way to make this usable by other PETSc users? You know, as a sort of options to PETSc, be able to turn this capability on?
So yes, I mean that is what we're trying to do. So I think that with a little more work, we could do the GenEO coarse space for all the ASM type preconditioners, provided that you also know these local Neumann operators. So provided that you have the matrix in some kind of mat.is format, or maybe overlapping mat.is format, then yes, very easily.
Yeah, the main limitation is just to have access to the element assembly of it.
Yeah.
That's what I was going to ask. That's the only limitation of the field. If you have access to element assembly, you can do it. Because you can compute the overlap, you can do element assembly, and then you want an eigenvalue socket. So this kind of method can be just a plugin for PETSc, but not use PETSc unless you incorporate.
Well, the adaptive multi-preconditioning doesn't use the eigenvalue solver, which is an advantage of that method.
So maybe eventually we will need some matrix format that is even lower level than mat.is and can store. We are working on that, I think. We were planning to work on that. It shouldn't be that hard to have a fully unassembled matrix class that keeps track of element matrices, indices, and can eventually be converted to mat.is, mat.ij, or whatever.
Yeah, but I don't want the assembly process going all the way into the solver. I want the solver to like ask for what it wants. Like I want the thing assembled this way, then I redo the assembly and give it back. Instead of shoving all of the assembly technology into the solver, I think it would be wrong.
But
Then you have to have a way to describe it.
I think that if you have sort of a mat.is format with overlap, then that's what you need.
Okay, so I think we should cut to caffeine and thank Nicole again for her talk.
Thanks.